Record. Yes, tak for det. Ja, jeg er. Ja. Så vi starter i dag, som jeg har begyndt at sige. Tak for det. Så det vi kom fuldstændig ind i linear regression. Vi skal have noget manuel beregning, og den vi skal vise samtidig, hvordan det kører i Excel, og den vi skal fortolke disse her resultater, og det hele hænger om noget, som er kaldt least squares method. Og det er nødvendigt at skifte over til engelsk her. Det var en lidt frys i min skærm. Okay, jeg er tilbage. Okay. Min skærm frysede lidt, og jeg var bange for, at vi har mistet kontakt. Men jeg er nødt til at skifte engelsk. 2 år siden, at det bare bliver mere og mere advanceret emner, som jeg kender bare på engelsk. Jeg kan ikke bruge så meget tid til at skifte hele år til dansk. Og også vores tekst, vores læsebord på engelsk også. Og det kommer, at flere og flere ting bliver på engelsk. Så jeg er nødt til at skifte over til engelsk. Og også en stor del af min gamle læringsmateriale fra kurser, som jeg har undervist i USA for flere år siden, det er også selvfølgelig på engelsk. Og så jeg kommer nu, det første få uger, det var ny materiale, som jeg lavede. Men nu har jeg mere og mere materiale, som jeg kan genbruge fra mine gamle kurser, og det ligger på engelsk. Så det kommer til at blive mere tekst på skærmen på engelsk. Og jeg er nu også måske til at skifte sprog til engelsk, fordi det er lidt for meget for mig at beskrive noget på dansk, som ligger på skærmen på engelsk. Så men jeg er ikke sikker på, som har sket hver gang her i den her semester, jeg er ikke sikker på, hvor lang tid den her tager. Så jeg synes måske, vi kommer næsten 3/4 vej frem. Jeg er ikke sikker på, at vi kan nå det hele i dag, men det er helt fint. Vi bare stopper, og vi kommer i gang igen næste uge. Så det, vi skal ikke bekymre os over det, vi skal ikke blive stresset. Vi bare når, hvad vi kan. Yes, yes, optagelse er i gang, og jeg er i gang, og jeg har min kaffe, og jeg er klar, så værsgo. Yes, lidt opvarmning først. Vi skal få vores hold i gang. Vi skal dyrke vores hjerne. Ja, så der er nogle data her, som jeg fremviser her på skærmen. Der er nogle data fra metroen faktisk, fra Nørreport station metroen. Fra en papir, som jeg er faktisk i gang med at færdiggøre. Med nogle af jeres mere ancienne kammerater, som er faktisk færdige med deres afgangsprojekt, og vi er i gang med at lave en journalpapir ud fra deres afgangsprojekt. Så i hvert fald, så her har vi nogle data, og vi har på blå, har vi passagertal til hver team for Nørreport station. Og den på orange, har vi det samme passagertal efter covid i maj måned sidste år. Så spørgsmålet er, kan vi bevise en ændring? Kan vi bevise, at der er en forskel fra før covid til efter covid? Og så jeg trykker her på det næste billede, som har en stor figur og lidt mere forklaring. Ja. Er det en forskel eller nej? Eller ej? Er det en forskel eller ej? Og jeg trykker tilbage her til det. Ja, okay. Og se her, når jeg har skrevet data. Så før covid har vi samlet, har vi prøvet data, har vi indsamlet data fra tirsdag, onsdag, torsdag i 2 uger. Klar? Got it? Tirsdag, onsdag, torsdag i 2 uger. Før covid har vi indsamlet data. Efter covid har vi indsamlet data tirsdag, onsdag, torsdag igen kun 1 uge. Fik det? Okay. Så, og se her vores store figur, vores store diagram, som viser det datatal. Og den her er vist som procent af dagen. Så for eksempel her på klokken 8, det siger ud, at før COVID, det var 10% af dagens traffic, som skete klokken 8 i Nørreport station på metro. Så spørgsmål her, kan vi bare sige her for eksempel, at traffic er mindre efter COVID, eller ej? For synes I, og vi bare tager en kort gruppearbejde her, og vi vender tilbage. Så ret hurtigt her, ikke for længe. Ikke længe nok til at få noget mere kaffe. Ja, du skal alle have mere kaffe. Vi har en kaffepause lidt længere i programmet, men nu er det bare en kort breakout room. 3 minutter. 3-4 minutter. Ikke længe nok for mig til at finde mere musik. Så vi starter her. Breakout rooms. Okay. 18, og det kommer ind til 4. Det bliver 4. Vi kommer lidt. 4 grupper. Yes. Så ret hurtig break her. Hurtig pause. Kan vi bevise noget ud fra den her data? Jeg vil ikke stoppe optagelsen, når vi går på pause. Fordi flere gange har jeg glemt at genstarte optagelser efter pause. Men så det vil blive nogle lang afsnitter ind i optagelser, som er bare selvfølgelig bare mørk skærm eller så jeg pauser ikke optagelse igen. Jeg bare holder i gang helt gennem alle vores pauser. Så undskyld. Så vi optager her, og jeg holder det hele tiden. Fordi hver gang vi tager en pause, hvis jeg prøver at stoppe det, jeg bare glemmer at genstarte det. Undskyld. Okay. Så så vi har, så hvis man tager den her spørgsmål og laver tegne en figur, som jeg har anbefalet flere gange, tegne en figur, vores rejection regions, vores confidence procent, vores alpha, og den tænker, okay, nu skal jeg tegne ind, okay, vores critical value, som ligger længere over til højre. Eller, til højre. Vi skal tænke her kun med absolute value. Så længere over til højre. Og den, vores teststatistik, som, jeg fatter ikke, hvad det endelig bliver til, men det er ikke så stort. Det er ikke så stort. Og jeg synes, at det bliver en meget små teststatistik. Så at, det er meget, i går, så opgaven fra den uge, vi gennemgår næste uge, efter jeg har vurderet dem. Så det bliver en uges mellemrum. Fint. Så her, det giver mening, hvorfor vores prøvestørrelse er vigtig. Fordi hvis vi har en meget små prøvestørrelse, det bliver meget sjældent, at vi kan vise nogen effekt. Uanset det er faktisk en effekt, som, jeg tror, hvis vi har mere data, Jeg tror, hvis vi havde det, hvis det havde taget data over 3 uger, Tuesday, Onsday, Thursday, i 3 uger. Okay, ja, det passer. Det vil blive n equals 9, og hvis vi har n equals 9 og begge to, jeg tror, at vi kan faktisk bevise til en satisfactory mål. Men her har vi ikke nok, og det kan være, at vi alle kender, hvor godt hvad har sket her i covid-tiden, og vi kan alle kende, at ja, det giver mening, at færre rejser med, i myldretiden. Det er noget, som vi tænker bare indre, at ja, det er rigtigt, men vi kan ikke rigtig bevise det ud fra den her data, så det er noget, som vi skal passe på, og det giver mening af, hvordan vi skal køre. Og det giver mening, hvorfor vi skal lære alle disse her ting, for det vil komme i fremtiden, og have sket i fortiden. Rapporter, undersøgelser, som har sat frem nogle forslag, eller nogle afgørelser, på grund af nogle små data, som de har samlet, og at lave nogle flot billeder og nogle flot figurer. Og vi skal ikke bare køre og lave beslutninger. Vi skal ikke bare køre og lave beslutninger ud fra en flot figur. Vi skal have noget science. Vi skal have noget scientific årsag til, hvorfor vi har lavet vores beslutninger. Er der nogen, som har en spørgsmål, eller er det bare en sofa squeak? Ja, okay, så vi kører videre. All right. Yes. Yes. Okay, linear regression. Og så her vi skifter lidt til engelsk. Så hvad for noget er den her linear regression? Ja? Så vi leder efter en linear regression mellem vores mål, mellem vores data. Så jeg skifter her. Så inputs. Så vi har selvstændige mål, selvstændige data. Vi har independent data, independent measures. Så data, som vi har bare gik ud i ekstern, gik ud i landet, målt på nogle mål, measured in some way. Ting vi kender i forvejen, things we know in advance. Så jeg siger det, fordi hvis vi bruger den her linear regression til hvad er det kaldt? Så allerede så jeg har glemt dansk. Så til forecasting, som er ikke det samme som på dansk som forecast. som jeg har fandt ud. To future trends, to figuring out to future trends, forecasting into the future, which is not the same as the Danish word for forecast. And we have our outputs. Yeah, okay, all right, yeah. All right. But if anybody, hvis der er nogen, som kan ikke rigtig forstå, hvad jeg har sagt på engelsk, bare brug ind og siger, Steven, jeg kender ikke, jeg ved ikke, hvad du siger. Okay, but anyway, here we go. So outputs, so we have our outputs, and all the examples you were going to do, and almost all of the research, it's almost always we're worried about one output measure, almost always. The number of times that we have something more complicated going on with two output measures is not that often, and not likely to be something that you experience unless you get way up there, something really advanced. So we'll just assume it's always going to be one output measure. Let's just go with that. So anyway, and then we want to estimate these causes and effects. We want to get a sense of, is it a big cause and effect? Is it a small cause and effect? Or, you know, how strong is this relationship? And we're going to do all this. So here's an example here, really basic example. This one comes from my old university in America. So we had this, so a typical American university, typical American small university, right? Just like in the movies, you know, footballs and football, American football and parties and Greek societies, sororities and fraternities, the whole deal. You betcha. And so we had, you know, a whole area of campus housing, residential housing for students. Almost all the students lived on the campus, like on the campus, not like in the same town, but I mean on the campus. And we had campus police. There was actually, at many universities, they have their own police force that is authorized by the state. Anyway, so we have campus housing, and we have students living on campus housing in a place called the ghetto because the housing quality was so bad. But you can make a linear relationship between the electric bill, the electric consumption, and the number of students living in the house, right? I mean, that's a reasonable linear assumption. You can make a formula for this, and this would be a very typical kind of linear regression exercise. What is the relationship of the electric bill to the number of students living in the house? And it's very likely that the relationship is that there's some kind of fixed basis electric consumption that's there all the time, even over vacation, even over summer. It's always there because it's, I don't know, it's refrigerator and security system and outside lights, stuff like that. And then you have the consumption from the students: television, stove, air conditioning. It gets hot in Ohio. You need air conditioning, and other things, you know, electric hair dryers and stuff. So you have this additional electric consumption that is per student, and you can make a linear regression. You can do a linear function and create, you know, collect the data over a year or two, and then plot it all and make a linear regression. So, and I just finished explaining all of this. So, but this is what we want to do in our very beginning introduction here, and then later in more complicated, more advanced ways with a lot more things going on. But at the very beginning, this is really what we're doing. At the very beginning, we have an effect, our electric bill, and we have an input. How many students are there? And we want to plot this and create a linear relationship and then measure it properly. So here we have this very standard beginning first simple linear regression. And this is starting on page 56 of your textbook. So we have the output variable y. We have a fixed value called the null beta, which is just a fixed parameter. This is in the electric bill. This is just that electricity that gets used no matter how many students are in the building. And then we have our variable function. We have our first parameter, our beta 1 parameter, and this is going to be how much electricity on average each student uses. And then we have an error term. We have an error term to the right. And the error term, as I've mentioned before, but I'll mention it here, the error term is, we call it error. It's not like error like you made a mistake, dummy, you got it wrong. No, it's not that kind of error. It's error like all the stuff we don't know. It's like it's just a big span. It's just a big bucket for, here's all the values. We don't know where the hell they came from. We're just going to put it over here in the error column. And you know, and so it could be small or large, just depending on how much information do we really have? Maybe we don't have enough information. And a really fundamental thing, and I've mentioned this before in some previous lecture, it's on the previous slide somewhere, I think maybe the first day. This error, we assume that this error is centered on 0. We assume that the sum of these errors over a very large data collection will be 0. There'll be some positive errors, there'll be some negative errors, and positive and negative, and then whoop, they come together and the net result is 0. This is really important. And if you think about it, if it was not 0, that doesn't make any sense. If it was not 0, then shouldn't that value go into the beta null, right? I mean, we already have a function in the equation for a fixed value. So it doesn't make any sense. Why would the error part have a permanent upswing or value when we would just take that and put it over in the beta null parameter? So that's important. And again, I've marked here on the textbook what page number this concept comes from. If you haven't seen this before, we haven't, I hope you've seen this before, the big capital letter E. The capital letter E, right? That is a standard mathematical term. It stands for expectation. It is what you expect, what you forevent. It is what you expect the value will be. It is another word for middle varity. It's another word for mean. And if you dig really, really deep into statistical theory, into probability theory, okay, yeah, there is actually a small difference in meaning between expectation and middle varity. But it's essentially the same from our level of knowledge. It's basically the same. But if you really dig and get really high up, yeah, okay, there's a little difference. There's a little technical difference, but we don't need to worry about that. So anyway, so down here below at the bottom of this slide, finally we have this thing. So if the expectation of the error is 0, then the expectation of this formula for linear regression, it drops down to just the beta null and the beta 1, right? Because if the expectation of the error is 0, then the expectation of this formula is that the error is not there. And so then down finally at the last line, we have what is called the fitted equation. The fitted equation. The fitted equation. So notice there's a shift here, and this is, I know this is really technical, right? And this is not so critical. You're not gonna like totally ruin all your work if you goof this up. But there, notice I shifted from a Greek letter to a Roman letter. Ooh. So I had a Greek letter beta before, and now I have a Roman letter B. So it's a small difference. So the Greek letter beta refers to the theoretical formula that I am setting up. It refers to the statistical, it refers to the formula as a statistical concept. And then the Roman letter B, that's the actual number that I got out of my Excel spreadsheet. So it's a small difference, right? They're basically the same thing, but it's just a shift in the notation to reflect what the hell am I talking about, right? What am I talking about right now? So when I shift to the Roman letter, I am actually talking about the actual value that I got from my actual data, as opposed to the theoretical, as opposed to this imaginary theoretical concept of the equation. You see that a lot. That happens a lot in a lot of statistical and mathematical fields. That does happen. You will see this reference to Greek letters for the theoretical construct and then you come down into the actual data that you actually have, and then they shift. And they shift to Roman letter to kind of show, well, wait a minute, there's a difference here between what we're talking about. Anyway, so that's the fitted value. So that is the actual equation we got from our analysis. And we need to remember that because that's going to come up again here. We're going to see that again in a couple of slides. So remember that fitted value, the Y hat, Y letter, character letter Y with a hat over it. That's the fitted value. Let's remember that because we're going to see that again. So what we're doing here in these next few steps is about the estimated regression, right? It's the estimated regression. Why is it the estimated regression? Well, remember, it's just a sample. When we do all this, we're not saying that we absolutely positively, we know for a fact that this is the way it goes. No, we don't. It's a sample. It's just the data you have is a sample. You got it from somewhere. In most cases, it's a sample. There are a couple of cases, for example, some of my own research where I have argued that no, it's not a sample. It is, in fact, all the data. And that is an argument between grumpy old men about what numbers really mean. But in most cases, in most studies, it's a sample. It's not the whole data set. It's the sample of data that you collected on the morning you decided to get out there and do it. So it's an estimated regression because it's an estimate based on your sample, which may or may not be true because you didn't collect all the data. You only collected a sample of data. So we call it the estimated regression. And then we go through all these exercises to kind of prove or to test how good is our estimated regression. So anyway, let's go here. And all these Werktoi, all of these things we learned in the last 3 weeks, they're going to keep coming back. If you thought, I finished that exercise, I'm not going to do that again. It's coming back. It's not going away. You did not get to run away from it. It's coming back, guys. So here we go. Least squares method. The least squares method, and this is also called by many people ordinary least squares, Elminley least squares, ordinary least squares. Sometimes people use ordinary least squares as a criticism, like you just used ordinary least squares. You don't really, you didn't work hard enough, but I mean, it's a very standard. I mean, it's the most fundamental thing in regression. So least squares method. So here we go. So the goal here in least squares is to minimize the error. It's to minimize the error. And the error is the difference between what our actual data says and what the formula that we created says it is, right? The Y hat. The Y hat is what our formula says it is. And then the Y subscript I is the actual data that I actually wrote down on my piece of paper. And I want those to be as close as possible. The closer they are, the more useful, the more accurate my regression is. So my goal is to minimize that. And how am I going to minimize that? I'm going to minimize the square of that number. Why am I going to minimize the square? Why not minimize the sum? Why not minimize the cube? Again, that gets really theoretical, but I took a course and learned this, and you can actually show that the square is the most vernufty, the most practical measure to use to kind of get what you really want. And one of the benefits of the square is that it kind of penalizes more extreme values. So you have data, and then you have like a couple of points way up here, And those points way up there, they're going to have a big impact, and they're going to swing your regression line. And you can argue about whether that's a good thing or not, but it is important so that your final formula does think about these heavy influencers, these heavy points up in different spaces. Anyway, and look, we're looking at a square. We have a statistic that's a square, and wow, okay, so now we're back to work Vertoi 5, Vertoi Fem, right? Because we need tools. We need tools that can make decisions, that can reveal information about measures that are squares. So yeah, we got to do that. So here we go. So here's the difference between our course and a, you know, heavy duty candidate level statistics class, right? In a candidate level statistics class, you know, I'd spend a couple hours and we would learn how to derive this thing. Yeah, we would learn, how did you figure that out, Dr. Herod? No, we're just going to accept this as given. I'm just going to tell you this is what the formula is, and you're just going to believe me. So these formulas will calculate the correct parameters for B null and B1 from your data that will in fact deliver a result that is in fact the minimization of that error on the previous slide. Full stop. Just trust me, it does. You know, it just does. And these are you know, fundamental. These are the formulas that do it. And what's in this formula, right? I mean, so everybody understands what we're looking at here, right? Summation, the sum of all this stuff. This unit, you know, this is the actual X data, the actual point from your data, minus, where did my mouse go? There it goes. Minus the mean, the middle verity of that X data. Get that? My mouse is, am I moving my hand? Here we go. Here's my mouse. I'm going to get a pointer. There's a point. Spotlight. Let's do that. Let's try this. Woo-hoo-hoo. Nifty. All right. So the actual data minus the middle verity, and do that over again for every one of the data points, times the actual data, the actual output data, minus the middle verity. And you're going to do that. This is a summation. So you're going to sum that over every one of your data points. Every one of your data points, you're going to calculate this. Divided by, again, summation. So you're going to do this again. So you're going to do the input data minus the middle verity, and that value squared. And this formula, you do this on your data, and that will give you the value of this slope parameter. It's called the slope parameter because it tells you what the gradient is. It tells you what the steep percent is. So that's going to give you that value. And then down below, it kind of stands to reason. You can prove this. The funny thing is, once you know what B1 is for a linear regression, once you know what B1 is, then B null, it just is automatic. It just comes, it's just what it is what it is. So B null just becomes the mean of your outputs minus B1 times the mean of your inputs. And that becomes very simple. So, and let's go to the next slide. We have an example. We have a little example here. Now, this example is a toy, right? This is like just a classroom exercise. This is just a toy. It's not really, well, it's not really recommended that you actually try to create any kind of research or any kind of solution based on n equals 5. And I say that even as myself attempted to do exactly that on a paper I tried to publish last year because I had no choice. I literally had no choice. But generally, it's not a good idea. Generally, you need more data. Generally, this is not enough data. but it's purposely a little small data set so that we can do this exercise, so that we can do this calculation here in the class time. So yes. So here's what I want you to do. So take that data. Come on, there we go. Take that data, and there's not a lot of data there, so you should be able to quickly type it into Excel. Take that data and plot it. And this shouldn't take very long. It should go really quick. But plot it, and then we come back, and I want someone to show it to me. So and I will not stop recording. I will let the recording run, but very quickly, not a lot of time here, folks. Let's just do this quickly. Go into your breakout rooms, plot this sucker, and I'm gonna pick someone and say, hey, show it to me. So let's do it. Let's go. And I will assign the people who are joining us late. Here you go. Boop, beep, beep, boop, beep, beep, boop, beep, beep. Yeah. All right. Do it. Do it. All right. All right. All righty. So how about Itzham and Milal and Natasha? What do you got? Show me your. Who does the bell ring for? The bell rings for you. All right. Yeah. Perfect. Yep. Yep.
Can you see?
Absolutely perfect. It's a little small. I know what the answer is, but the other people don't. But it does look correct. Yeah, it's coming. Yeah, there you go. Yeah, of course it is. Yeah, that's correct. So there we go. So yeah, that is perfect. Thank you very much. Thank you for your participation. You win a prize. All right. So now next. So there we go. So there's the plot. Now I didn't plot the line because that's a little cheating, right? We don't want to go forward. Hey, wait a minute. You know, we're not doing that yet, right? We got a few things to do first. But so that's the plot. Here's just the plot of the data. Now, this is actually not just you know, a bunch of busy work. This isn't just, you know, some tussle arbeit that just say, yeah, actually you should do this on a regular basis. When you have an exercise, when you have a problem and you're going to apply some tools, some linear regression or something, you really should do this. You should plot your data without any other work, no other analysis, nothing. Just plot it and take a look at what you got and try to get a picture of what's going on before you start slicing and dicing and doing stuff to it. Really, you should. And that should be just a standard thing you just do, because you could learn something right from the very beginning just by looking at the picture, just looking at the plot of your data. All right, so there we go. And yeah, so now let's calculate B1 and B0. This takes a little bit more work. But you do it in your spreadsheet. You got your data. You're gonna, you got to calculate the mean of X and the mean of Y, and then you got to lay out a lot of rows and columns and calculate all these differences, and then, do the multiplication and then sum them up and then take the values and then do the division. It's a lot of, it's a little bit of busy work, right? But it's just good, important that you do this once at least so you have a sense of what's going on. So you're going to go back. Let me go back, remind you. This formula, these two formulas, take this data and calculate these two formulas. Do that. And then let's see the results. Let's see the results when you come back. All right, so let's do it. Here we go.
Ja, det kan også godt være en mulighed, men altså.
Alrighty. Looks like group one is still thinking a little bit. Alrighty. Whoop. Somebody said something. I mean, that was just a child. But that's a lot of fun having kids at home while you're trying to take classes. Those were the days. I'm an empty nester now, but I remember what it was like to have two young kids running around the house. That was 20 years ago. Yes, indeed. All right. So how about it? How about Jonas's group? The other two Jonases. Look at that. Yeah. The Jonas Power Pack. Yes. Oh, here we go. All right. Beautiful.
Yeah. So this is the result.
Yes. Can you zoom in a little bit? It says really small. It's really small. Okay. I don't have another set of glasses I could put on to see this. This is it. I only got these glasses. Yes, indeed. All right, folks. I can confirm that those are the correct values. So excellent. So, and then, and there are different ways, this is just a manual exercise. This, someone else out there, maybe you set up your spreadsheet a different way. That doesn't matter. It's fine. As long as you can make sense of it, you know what the heck you were doing, and, you can keep track of it all. I did mine a little differently, but it's just a matter of cosmetics about how you structure everything. So I'm going to show mine here now. Yes, and I'm going to boot you out. Yes, goodbye. And so here we go. And yeah, so here's how I did mine, right? It's just an exercise. It's not, critical. But so here I just spread out all these calculations and I just did all these separate numbers, and then sum them all up. And there you go. So there's the answer, right? And again, this is, just to give you some appreciation for all the wonderful things your software does, but also so that you understand where these things are coming from. So now we want to do the residuals. The residuals, the remainders, the leftovers, well, I can't think of anything funny to say. Anyway, so we want to find out the difference between this formula that we just created and the actual data. We want to see how close a fit it is. We want to see how good it is. And residual diagnostics is really important. And I'm sorry to say that it's not taught a lot of times. And I think that's wrong. I think that's really bad, actually. It is not taught. And I have seen presentations. I have seen research presentations of various kinds of regression models or whatever, and where the residual analysis was not done. It wasn't done. And that's wrong, because there's stuff that can be hiding. There are things that can be hiding in your residuals that might actually tell you that your model is not so good. So it's kind of important. We should be doing this. So what we want in the residuals is we want a nice cloud of points. We want just a nice cloud of points. We don't want any pattern. We don't want some kind of clear shape, because if you see a pattern, if you see a shape, it means you forgot something. It means, honestly, it means that you didn't do everything that you could to finish your model. So here we go. I got to push the right button. There we go. So now you've got your formula. Now you need to calculate the fitted values. the fitted values. I want you to do, where is it? Come on, it's here somewhere. I had it on the screen in one of these slides. There we go. Yeah, this one. I want you to calculate this formula in red at the bottom. I want you to calculate these fitted values. And then I want you to plot the fitted values and the actual values. You know, you can reuse this picture. Plot the fitted values on this picture. What are the fitted values for this actual data? So let's do that quickly. And we come back and repeat this cycle. And then we're probably due for a little bit longer break here for a coffee pausa here. Actually, well, let's just call this the coffee pausa. So I'm going to set the breakout rooms, but then I'm going to set the egg timer here for 10 minutes. Well, yeah, 10 minutes. I'll set the egg timer for 10 minutes. So we got a little bit more of a break here. So let's go. See you in 10 minutes. I'm going to set the egg timer. Oh, someone's writing to me. What are you writing? I guess I answered your question. All right, there we go. Yes, indeed. All right. Yes, indeed. And I got to, Natasha, I got to put you in somewhere. We're going to put you. All right, how about this one?
Jeg er i gruppe 3, Steven. Jeg røg bare lige ud før.
Okay, vil du gerne blive i gruppe 3? Det kan jeg
Ja, lad
godt.
mig bare.
Det kan jeg godt. All right. Good. All righty. Yeah. Yeah. Yes, yes, yes. Yes, yes, yes. All righty. So, all righty. Richmond, all right. How about Isabella? What do you got?
Ja, altså, vi har lavet det sammen på Christians computer. Så han deler lige sin skærm.
Ah, yeah. Yeah, oh, flot. All right. Yeah, so this is correct, right? So, and it just happens to turn out that a couple of the points overlap each other, and that's just the way it is. And that happens, you know, we have such a small data set, and we have this data set is a little bit of a cheat in terms of our rules, our regulations on linear regression. One of the rules we have is that the data is supposed to be continuous. The data is supposed to be real valued. And obviously it's not here. This is integer value data. This is integers, whole numbers. So, but that happens a lot. I mean, when you're doing transport, for example, the passengers are integers. When you're doing a regression on, you know, how many passengers bought tickets to go to this place when the ticket price was such and such, and, you know, the weather was nice, the weather was 20 degrees out or whatever. Thank you. And lots and lots of studies, almost all of them, you know, do things like that, right? Where they're measuring passenger counts or something, and passenger counts are integers. And so we violate this a little bit in our regression models. It doesn't, this particular violation isn't the end of the world. It doesn't, you know, it's not a horrible crime, but it is a little bit of a violation. And if you get really, if for some reason it becomes really concerning, there are tools to deal with it. And we will see some of these tools later. For example, logit regression, where we will have tools that specifically deal with data that is not real valued, data that is integer valued. And this kind of messes up some of the statistical assumptions. It messes up, it kind of irritates or urlegs the you know, the normal distribution assumption of the error and stuff like this. So yeah, so this solution here, and I'll pop open my, come on now, where are we? Where's my, here we go. I'll pop mine back on the screen here. Yes, and so here's my, you know, my version of that picture, right? So the blue is the original data, and the little orange crosses here are the fitted values. And at x value 1 and x value 3, there are 2 fitted values over top of each other. So that's, you know, that's because the data is integer valued. And so we have lots and lots of values that land on the same exact data point. Anyway, so, yeah, okay, great. So now calculate the error. Again, this should go really quick. So like 2 minutes. I mean, I'm just going to hit breakout rooms, calculate the error and plot the error. And so really quickly, this is not a long break at all. So here we go. Do it, please. And we will, I won't even get up from my chair. I'm just going to sit here and wait until you got it. And then, so click, 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 do it. Come on back. I think we got it here. All righty. All right.
Jeg ved ikke helt med plot der. Det forstår jeg ikke helt.
Okay.
Når vi
All righty. Who wants to try it? Let's see something. Who's got it?
Vise det, eller vil du bare have nogen viser det, eller har du valgt nogen?
Yeah, come i gang.
Ja, kom i gang. Så.
Oh, nice.
Brug den der formel. Altså vi udregner den heroppe.
Yeah.
Og så er det så plottet ind.
Yeah, that's right. That er præcis, hvad vi leder efter. Yes. Can you zoom in on that? Because there, you know, again, everybody's eyes. Yeah, let's do that. Yeah, there we go. That's right. That's what it is. That's right. So this is the residual plot, guys. This is the residual plot. This is the plot of the errors in our regression. So we have fitted this equation, and this is what's left over. This is the stuff that, it doesn't fit. It's leftover deviation that we don't know exactly. Okay, I don't know, you know, it's just different. I don't know why it's different. Is it random error? Is it measurement error? Is there some effect out there that we don't know about? Was it raining on the days these cars were sold, right? I mean, like on so on the, you know, on the one where there's see, what is it? It's number of television ads, right? So the first data line here is one television ad, and for some reason we sold 2 more cars on that day than on the day where there were 2 television ads, and for some reason we sold less cars. or let me think for a minute. What's the equation? It's y minus fitted. So which way is which? I gotta think about that. I'm making statements. I want to think what I'm thinking. This is we sold fewer cars. We sold fewer cars. So negative is yes. So that I am saying it correctly. I am saying it correctly. Yes. So for some reason, on the we have 1 ad, 2 ads, or 3 ads, right? And for some reason, on the 2 times that we did 1 ad and the 2 times we did 3 ads, there's this different effect. And what caused that different effect? I don't know. The salesman was better that day. He was a smooth talker. He knew how to sell cars. Who knows, right? So this is this error. Anyway, thank you very much. I will come back in now, and we're doing good here. This is great. This is really good. All right, and we are catching on here. Everybody's figuring. There's my picture, right? And this is a good one. This is great. And I mean, it's very, it's just a classroom example. It's not like the most advanced model in the world, but in theoretical terms, it's good. There's no trend. There's no pattern. It's just a random bunch of plots, and that's what we want. When the residual plot is just kind of random like this, that's what we want to see. And there will come times where you will in fact see a pattern. You could see a bow pattern like this in the data, and that will be an indicator that you have more work to do, that you are not done, that you are not finished. You can also see a cone in the residual plot. You could see the plot make a cone like this and get bigger as one dimension changes, and that again will be an indicator that you have more work to do, that you are not done. All right, so I'm not going to take a pause here because we kind of had a pause already. But we just kind of, let's kind of get up. Everybody stand up. We just need to, we get a little stretch, a little bit. Everybody up. Just stretch a little bit, right? Okay, a little bit of stretch like this. A little bit of stretch like that. Come on, if you've been laying on the couch all day, sitting at your computer, it's too much. So just kind of stand for a minute. So while we're doing this, what is a good regression model? What is a good regression model? Okay, we gotten to the point we can do it. We've run through these equations. We can do this model. We can get an answer. We can see a residual plot. I've already told you what's good in a residual plot. But I mean, I can ask my dog Bo, but I don't know if he knows the answer either. What is a good regression model? And that's going to be the subject here of what comes in the next few slides, obviously. What is a good regression model? So let's think about this for a minute. What's a good model? What is this? All right. What do you think? What do you think? What is a good model? What makes a good model? What makes a good model? Oh, I got a hand. Oh, no, that's not. I thought I had a hand up. No, I don't. Okay. All right. What's a good model, guys?
En model uden for mange outliers.
Okay. Okay. Yeah. Okay. Yeah. Det kan være model, som måske vi kan vende den her udtalelse om lidt. A model, som ikke påvirker og så mange outliers. A model that's not so affected by outliers, right? Maybe because the outliers are they are what they are, right? They're in the data, and so we're stuck. We kind of have to accept the data, except for if we will see a way to look at this. There is a method to do this, other than just, hey, it looks like it. It looks like it, take it out. There is actually a mathematical way that I think we have time, as I think about our plan going through here the next few weeks. I think there's enough. I think there's a spot for it in our lecture plan. There is actually a mathematical way to look at this regression data and actually make an argument for, hey, you know, that one's an outlier, guys. That one's got to go. But yeah, so one that's not affected by outliers so much, that is a concern. What's another? Think about what else? How else can I seed this conversation? Stimulate this. But you know, what is the purpose of us doing this regression? So we're making this regression model because we want to do what, and what is it that makes that good? Any thoughts? Find similarities. Expand on that. Ulvil din idee. We're going to find similarities between what and what, or what do you think, Milal? Between data? Yeah. So a good regression. So I kind of started to point at it here, right? So if we look, I'm going to put this back up here now. Let's do this. All right, here we go. I'm going to make this thing bigger over here and move this thing over there and do this, that, and the other. All right, so we started way back here, right? Come on. There we go. Right, so this is our goal, right? Minimize the error. Well, that's a very explicit, that's a very specific, let's do this. So the implication is that a good regression is one that doesn't have a lot of error. And mentally in our head, think about that from both sides. I'm going to minimize the error. And then if I'm minimizing the error, I then must be maximizing what? What am I maximizing? If I'm minimizing the error, what is it that is becoming larger when the error is getting smaller? What is it? What am I maximizing? What is it that I've minimized the error, so that must mean I'm getting something else in exchange. What am I getting instead? That implies it's a good regression. Whoop, somebody's saying something. I got a trick on this. Come on, let's get this. Come on, here we go. There's that window. Where the window keeps hiding. These windows don't want it. Here we go. There's too many windows. Okay, a better result. Yes, that's what I'm. So what's another word for result? What is the regression model? What is the regression model doing? And it is kind of a result. That is true. And I think the word I'm looking for, if I could be allowed to put words in your mouth, effect, right? Effect, a better effect. So I'm looking for, we want to minimize error and we want to maximize effect. We want to a good regression model is one that is clearly explains and shows effect, shows power, shows that it's actually doing something. And power actually is a good word. Power, and in English and mathematics, it has a kind of a special meaning other than just, like power as in a multiplication power. That's not what I mean. It has another meaning, and that means the ability. It means the ability to be knowledgeable. It means the ability to say, the ability to make decisions, the ability to show results. So this power, sometimes we talk about the power of a mathematical thing or a statistical thing, and it generally means the ability of that mathematical thing to actually show knowledge, the ability of that mathematical thing to actually solve questions, solve problems. It's power. How powerful is this test? How powerful is this statistic? How much power does it have? How much might does it have to solve our problem? And there are differences. There are some mathematical tools that have a lot of power, and there are other mathematical tools that don't. And sometimes different levels of power according to what is the thing you're trying to solve. So that's what we're getting at here. So here, boop, 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 boop. Here we go, back to where we were. Come on, and next, and next. Yes, yes, yes. So yes, we want the error to be small. We want the model to have power in that it explains what's going on. So we want the amount that the model explains to be large in relationship to the amount that is the error. These things need to have a strong relationship, a large ratio, a large fourfold. But we don't want to create garbage. And this can happen. And this is something we will learn to avoid, and something we need to be careful about as we get more and more complicated in these things in the next few weeks. It is possible to take a bunch of data, do a bunch of stuff to it, create some kind of regression formula that gets really great high numbers, that looks like it's really super fantastic, and it's just garbage. It isn't worth a damn thing. And it's because you can pack the model full of different structures that kind of accommodate for all of the things happening in your data. And it makes it look really great. But when you start to test each little parameter statistically, like that slide I had at the beginning with the data from Northport Metro, you know, it looks great. It's a beautiful picture. It looks great. But if you actually then, say in a regression model with a lot of different moving parts, and you actually start to test those pieces, those little bits of moving parts, and say, is this thing real, or is this just my imagination? Am I just, am I just smoking something here, or is there really, what's going on? And sometimes the answer is, yeah, you're just smoking something. Sometimes the answer is, yeah, it looks great in the formula. It made a nice, pretty number, but it doesn't mean anything. It's not worth anything. And you need to pull it out. You need to take it out because it's not statistically correct. It's not valid information. And all it is happy juice making you feel good, but it actually isn't statistically valid. And it's actually not really making your model better. And so we will see more examples of that. We saw some examples that was essentially buried. Well, not buried, but I mean, not obvious to you. It was obvious to me, not obvious to you in that paper we read from Lee 2016. So that paper on delays at train stations. So a big chunk of that paper, a lot of the work in that paper is going through all this data and saying, okay, does this data actually contribute to the accuracy of our model, or is this just filler? Is this just making the model look good when it's not? And that's part of that work. So anyway, let's move on this baby. So now we have a new work toy here, work tool, werktoy. This is our 8th werktoy, and we're going to have an ANOVA table. ANOVA, fun little word, stands for analysis of variance. Analysis of variance, ANOVA. So we want to, this ANOVA table is going to answer this question. This is a question of, I want how much of the data, how much of the knowledge is coming from my model, and how much of the knowledge is coming from error. And I want to compare these two. And I want to come to a decision about whether the model is strong or weak. How strong or weak is my model? And the ANOVA table answers that question. The ANOVA table gives information about how strong or weak your model is. And so it's really a fundamental thing in a regression analysis. So here we go. Once again, we're going to do this based on squares. So we're interested in square statistics. So again, this is why it was so important to go beyond just the normal distribution and the central limit theorem. This is why we went to work toy, 5 and then 6 and then 7, because we needed that tool to do studies on squares, numbers that are squares, quadrature. So here we go. So this is this fundamental piece of information that we really want to look at. This is the sum of squares relationship in our linear regression, our sum of squares. And we're going to calculate these sums of squares and compare them to each other. And it's going to be really important. So you basically have from the left side, you have what's called the total sum of squares. So the total sum of squares is the deviation on the output variable. So, and you can see it right there on the screen. You can see the formula. So it's the actual data minus the mean, the middle variety of your actual data squared. And this is a kind of measure of the variance of the output, essentially. This is basically a measure of the variance of the output. And then, again, this is something that I would do in a really theoretical class. We would do this, but here you just got to trust me. You just got to trust me. It's correct. I can show you that this formula is correct. I mean, but it's okay. If you're really curious, you can try it yourself. It's not that hard. But that part on the left is equal to the part on the right. And the part on the right then is, the first part is the sum squares of regression. So that part sum squares of regression, that is our y hat function, our fitted value, minus the mean of the data, and that is squared, and that is a representation of the variance of our fitted function. And then to the right, there's our friend, the error term. There's our epsilon. There's our error term. So to the right, we have our error term, our epsilon, and we're going to square that. And it turns out, and that is going to give us a picture of variation around the error term. So we have variation on the regression, our fitted function, and we have variation on the error term. And those two variations, when they're squared and added together, they are equal to the variation on our original data, the variation on our original data. So this is really fundamental. This is a really big deal, because these are squares, they're statistical, they're quadrats, and now we can apply some statistical tools to study this and give us some questions about whether these two things are equal or not equal. If they are equal, for example, if the variance around the regression is the same as the variance around the error, it's basically saying, you don't know what the hell you're doing. It's basically saying, yeah, thanks for the pretty model, but it doesn't mean anything. It's just lots of pretty numbers on the screen. But if the variance due to the regression is large, and the variance due to the error is small, then you're saying, hey, wow, look, this is where things are happening. This is the power. This is, yes, your regression model is good. And so let's take a look at that. So this is the ANOVA table. This is the ANOVA table. And this is a standard format. Darn near everybody does it the same way. And most software programs do it the same way, with very small differences. Small differences, of course. Thank you, Bill Gates at Microsoft Excel. It's always Microsoft Excel that seems to lead the way in finding ways to present things differently than all your textbooks say they should be, which we will see shortly. So here's the ANOVA table. So we have the first column is the sum of squares values. And then the next column is our degrees of freedom. And so N is how many data points do I have? And then P is how many beta parameters are there in our formula? How many beta parameters are there? Now, for this whole lecture today, we are doing simple linear regression. So the answer is 2. There's never any different. Later, when we go to more advanced linear regression with more things going on, that number of parameters starts to change. It starts to get bigger. But right now, today, it's 2. It's 2 for the whole day. It's 2. So P equals 2 today. And then to the right, we want to calculate what's called the mean square regression and error. And then to the right, finally, to the last column, Bo's giving me the evil eye. He wants to go out. All right, hold on, mister. Finally, to the right, we have an F statistic. We have a statistical, a test statistic. And maybe I can say this right now and just get your head thinking. Remember, work choice 7 is all about ratios of squares, right? And we used it to analyze ratios of variance because a variance is a square. So here we have a ratio of squares. We have the first column is squares. The third column is a square. It's a mean square, but it's still a square. And now we have in the last column a ratio of squares. So ho, ho, ho. No, we don't get away from it. Now we have to go back and use work choice 7 again, because we want to test this thing. We want to test and see if this ratio is important or not important. If the ratio is important, then we have found something. If the ratio is not really important, then it kind of says, yeah, good, thanks for trying, but you lost this game. So let's go to the next picture here. So I want you to do this. This will take a little bit of time, not a horrible amount of time, but a little bit amount of time. I don't know if the amount of time I've been giving you is about right. I hope it is. I don't know if it's too much or too little. Seems no one has said to me, oh, I couldn't get it done. I didn't have enough time. So I think it's been enough time. So we want to create this table. And so you're going to go back and there's your formulas. There's your formulas. And we want to create that table by hand from this regression that you fitted and display it. So the sum squares, create the table, calculate the means, and what is the number in the far right column? What is the value in the far right column? So let's do this 5-6 minutes. Okay. So I'm gonna do this while I take Bo out. Bo wants to go in the backyard. I got to let him out. He's looking at me like, come on, Dad, open the door, damn it. So here we go. So you guys do on this, and I will be back. I will be back here. All righty. All right. Set the egg timer. There we go. 6 minutes. Here we go. All right. See you in a bit. All righty. So let's see what we got here. Let's go right back up to the top here, and group one here. What do you got? Mark and Thomas and Tua and Gunbjørn. What do you got?
Men nåede ikke lige det hele. Jeg skulle lige væk med datteren, så du må nok ellers spørge nogle andre.
Okay, all right. Joel and Isabella, what do you got?
Det
Vi
ligger
har
på
lavet
Christens
det
computer.
sammen med Christen. Og han var også i vores gruppe. Jeg tænker, yes,
All righty.
Vi har den her.
smukt.
All right. Just kind of Ulvil, you didn't scare him a little bit here. And yeah, oh yeah, there we're getting better. All right. Okay, yeah, and yeah, there's the answer right there. That little bit, if you kind of zoom in. Yeah, thank you very much. Oh, yep, very good. Yeah, all right, yep. Yeah, that's it. That's right. Yeah, that's correct. So, so here we go. So this is a standard ANOVA table, and this is correct. So you can kind of see right now, we have a relatively high ratio between regression sum squares and error sum squares, and that's a good thing. That's a good thing. So even and that's still a good thing, even though this is a really small data set. And because it's such a small data set, it is going to mess up our degrees of freedom. Our degrees of freedom here are pretty, they're not great, really. I mean, it's okay for a classroom exercise, but in the real world, if we were doing a test, these degrees of freedom would be like, oh my God, this is horrible. They would be just too much, too small. And then the F statistic is correct. Thank you very much. That is correct. So let's see now. Thank you. And so yeah, a little bit of a work, right? And so we will very shortly see that, of course, the software just does this all for us. And this will be the last time we have to do that kind of really manual grunt work on our own. So here we go. So of course, there you go. And you had the same thing. So there's nothing exciting to say there. So now we want to test. We want to do this hypothesis test, this hypothesis test, right? We want to do this. We want to test. I mean, you can look at those numbers on the ANOVA table, and you can pretty much just eyeball it and say, oh yeah, it's okay. But if they weren't quite obvious to the eye, or you need a little bit more, certainty over whether the results are correct or not, you got to do this test. You got to do this statistical test. And so what are we doing here? The test question here is the effect we are seeing from our regression model, is it really more powerful than the effect from the error term or not? And so that is to say, for example, in this is a copy of the picture from our last lecture from last time. Are they the same or are they not the same? If they are the same, if the effect from our regression is the same as the effect from the error, then it's like, yeah, we didn't do anything. This is, we didn't do anything. But if the effect from our regression is not the same as the effect from our error, then clearly the regression is doing something. The regression is clearly important. It clearly has a value. So we want to do this test. We want to do this test and show that the effect from the regression is not just dumb luck. The effect from the regression is, in fact, because this is correct. This formula actually has value. So what I have written in here on last week's picture is just, so this is last week's picture about testing variances. And I have written in onto it where the new values fit in this conversation. So last week, it was about just plain old variances. This week, it is about these mean square regressions, which are a kind of structure. The mean square regression is essentially almost mathematically the same as a variance, as a, you know, the variance that you know, the standard kind of definition of a variance. So we want to use this test statistic to make a question, to make an answer. Is this real? Is there really an effect here or not? And so in this case, this slide from last week, the null hypothesis was, okay, are these two things the same? And this week, today, right now, the null hypothesis is still these two things are the same, but our desire is to hear, we would like to hear the answer, no, they're not the same. That's what we want to hear. We want to hear, no, they're not the same. Because if we want to hear that, yes, the regression sum squares are different than the error sum squares, because we would like to hear that we have in fact done something, that we've accomplished something here. So you have this picture as a guide, and then we want to do this. We want to test this. And you've got the data. You have the test statistic. We just saw it. Creston just showed it to us. And we want to do this test. We want to do this test. Is the regression more powerful than the error? Is the regression a stronger information source? We want to do this at 5% significance. And this is essentially the same method as what I just showed you on the slide from Work 27. And you just need to kind of think about it in this particular context. So use the method of Work 27 and this information from the ANOVA table to, and I've presented it here too, and to calculate this this test. And the only thing that I can see now that maybe I should answer is where, okay, the question you might have is, where do the degrees of freedom come from? So these degrees of freedom down here, so you know, these degrees of freedom for the critical value, that is going to come from, come on, that is going to come from here. These degrees of freedom. It's these degrees of freedom right here in this column in the ANOVA table. This is the degrees of freedom for the regression. This is the degrees of freedom for the error. So those are the degrees of freedom that you're going to use in this critical value down here. In this critical value down here. And it's in that order. So it's degrees of freedom regression first, just like it is in this picture. And it's degrees of freedom error second, just like it is in this picture. Because this order matches what we did in the ANOVA table. Regression on top, error on the bottom. Regression first in the degrees of freedom, error second in the degrees of freedom, like that. Other than that, this is exactly the same as this method from last week. So do this and draw the picture. And then when we come back, I'm going to ask one of you to hold the picture up to the camera. Show us the picture. Let's see the picture. Draw the picture. Let's do that. So again, we're like 5 minutes, and I'll see you back in a minute here. All righty. All right. So if the, yeah, how about the last group, Lena and Rasmus and Jonas? What do you got? Where's your, how about your picture? Let's see your picture.
My dog ate the picture. I'm sorry.
Ah.
Yeah. But I
Who made
think
the picture?
Rasmus has a
Okay.
sharing his screen, but we're not quite sure how it's
Okay.
done. If we got the
I
right
don't know if
result.
this is.
So the numbers correct, but let's get a picture. Who has a picture? The number's correct, but you know, you gotta understand.
But then
this.
the picture is easy. You know, then we can do like this. Yeah. So then we have the function here.
Oh, you're very good with the mouse.
And then the critical value is here.
Yeah.
That is 17.
Yeah.
Point
that.
something.
Yeah,
And then
yeah,
the
yeah.
21 is down here.
Yeah, good.
And this is the reject region.
Yes, exactly.
So it has to be rejected.
Okay, now. All right. So, is this single-sided or double-sided?
So it's double-sided, I think.
It's double-sided, so there's another reject region over there.
Yeah.
And so how much percent is in the right tail?
2.5.
Right.
Yeah.
Right, exactly. And that, of course, you had that correct, because otherwise your critical value would be wrong.
Yeah.
And so what is the p-value for this?
I don't know.
What is the p-value for this, huh?
So actually the other region. Oh.
You erased your picture too soon. You should have just sketched it on the picture. Yeah.
And then it would be
Yeah, that's right.
this one and
That's right.
the degrees of freedom.
Mm-hmm.
I think it's 1.
Yeah.
And 2 must be. And then true.
3. It's the same degrees of freedom as you used before.
Oh yeah.
Great. Now
So
this, there's one step missing, right? Because,
oh yeah, we
and
have
this
to
is why
divide
drawing
by.
the picture is important, right? Because this value,
Yeah.
why is there a step missing? What is, this is why drawing the picture is so important. What is missing? What are we missing here?
If we draw this one again.
What's missing here? Thank you. Yeah.
We have 17 here.
Yeah, that's right. That's right.
And we have 21 out here.
Right. And that's right.
Yeah.
Yeah. And now, where is the p-value on this picture?
The p-value would be, I think when this is 98, then it must be out here somewhere.
Right, but go ahead and draw it in. Like literally,
I think
where is
because
it?
yeah, I think it would be around here.
No, because that's not what your formula says. That's not what you typed into the formula.
Then I don't know. But what do we need then? We need some.
Draw a line in, draw the line in where the p-value starts, and draw an arrow in telling me where the p-value goes. We need an arrow showing where the p-value is.
I have no clue.
So can I draw on this? I don't know if I can. Can I do that? No, I can't. I can't draw on your picture. I can't draw on your picture, but does anyone out there know what I'm driving at? What I'm trying to get
From 0 to 21. Up to level.
now, what is from 0 to 21?
This p-value.
No, it's not. From 0 to 21 is the number shown on the screen. From 0 to 21 is the number that that Rasmus is showing on the screen, and my complaint is that's not the p-value. What is the p-value on this picture? Where should the p-value be on this picture?
So we should have 1 minus. Or...
Yeah, because this again, and you get some more decimals. You need some more decimals on there.
Yeah.
It's not really 2. It's like, yeah, exactly.
Yeah.
So this is why drawing the picture is so important, everybody, because you want to draw the line in, and the p-value is to the right side. The p-value is that percent of how much worse can it get. So
Yeah.
from the 21.
So the first one I made the wrong one. That was the that was from here, the first one I drawn.
Right, exactly.
And the second one is this one.
Right.
So here.
Right.
Yeah.
And so it's just like I've shown you, you know, put the arrow in, draw a line, put an arrow saying this is what I want, because you know, so the function, the first function, the tdist function in Excel, it gives you that percent from 0 to 21.
Yeah.
But we want the part after that. We want the other part. That's the p-value. The p-value is that part that says, how much worse can this get? How much more is there to the extreme than what I found now? And so the answer is to the right, to Hoya, to the right of the 21, there is 1.9% more possible. And that's good. That's good because if we're going to do sometimes when people are giving reports, all they do is they just state the p-value. They say, oh yeah, the p-value is 2 point blah blah blah. Yeah, so I win. You know, so here now this is, and I've been presenting it this way on these double-sided tests because it's more important to me that you are very clear about what these pictures look like and what's going on. But very often in papers and in software and other things, you know, the way people want to think about it is they want to say, okay, I decided that I want a 5% significance level. And yes, it's a double-sided test. And that means, yes, the left side is 2.5% and the right side is 2.5%. But I want a 5% significance level. And I want to hear a p-value stated in such a way that I can simply compare it to 5% and make a decision. And so that means that this p-value that we just calculated on this double-sided test, it's 1.89%. I mean, that's just, it's just clear from the picture. But a lot of software programs and a lot of people will then state that, if it's a double-sided test, they will double it. And so they say, oh no, the p-value here is 3.7, you know, because they want a value that they can compare directly to the significance level. And it can get a little confusing sometimes, because then it also hangs on, is it single-sided or double-sided? And sometimes you just have to, it can depend on the specific way the software is phrasing the question. So I know I've lost about half of you with what I just said, but I just say it's so important that you draw the picture, because even if there is a misunderstanding, even if for some reason you and the person you're talking to, they aren't quite thinking the same way about how to quote these numbers, or that the textbook is encouraging you to do it a different way. If you draw this picture and you draw this parts in, there's no disagreement. There's no way that there's a disagreement. You draw the picture, you write the heck what you mean, and then you show it to somebody and say, okay, yeah, I agree. That's what I was thinking too. Even though somebody might say, oh no, you need to double that number. The number needs to be twice as much or whatever. And so this is kind of important. So anyway, thank you. And so let's roll here. We're doing really good. This is great. This is working out just fine. So there we go. There's my picture, right? There's my picture. And now, and remember, in this case, reject is a good thing. Reject is a good thing because in this case, the null hypothesis is nothing is happening. So rejection's a good thing, because rejection in this case is, yes, something is happening. Yes, this is not just random. There is, in fact, an effect going on here. So, so rejection is a good thing. So this is a positive. This is, yes, we do have a model that, in fact, functions correctly. So there we go. So that is very good. So now, here we go. Now I'm just gonna demo this. I'm gonna demo. So now we want to do this. So I've put you through all this hard work to manually calculate all this stuff, and you know, whew, okay, you won't have to do that again. We can automate this in Excel. So let me fire up Excel. I'm gonna fire up Excel on my computer and demo this. Here we go. And there we go. And let's do this. And I'm going to open this and get this open. And here it's coming. And I'm going to scoot this over here. Come on. And yeah, that's right. And then I'm going to open another one. And a blank one and put that over here. All right. Yeah, ding dong, ding dong. Come on. Anytime now. All right, there we go. I don't know why. What in the world takes so long to open a blank spreadsheet? What the hell? It's like, I need to think about this. I don't know what to do. It's got no data in it. You know, here we go. So blank spreadsheet. There we go. Now, let's see what's happening today. Okay. Now the tool we're going to use in Excel to do this is the data analysis pack over here. Now, there is a bug. There is some kind of software bug in Excel that is so annoying for me. Maybe it affects you, maybe it doesn't, or it may be that you have just never used this before, maybe. And so if you don't see this right now, you just need to install it. And to install it, it's File menu, Options, and this thing opens up, and it's down here, Add-ins, and then Manage Add-ins, and then Analysis Tool Pack. And you got to check this box and say, okay. And then, yeah. And that's, now I mentioned there's a bug from, I don't know why, but for my software, this disappears randomly. I don't know why, but it just, I could come back to Excel tomorrow and turn it on and try to work on this spreadsheet, and this will suddenly be gone. It'll just be gone. And the only way to get it back is I have to go back and reinstall it again. So I don't know if that affects anybody out there. It might, but just so you know, you're not alone. You're not the only one. It's really annoying. It's just, you know, to have to stop what you're doing and take a couple of minutes to go and reinstall the data analysis pack, and sometimes have to restart Excel, have to close Excel and reopen it. It just is. You know, I don't have a solution. It's just, it is what it is. So, all righty. So let's do this. Let's do this. Here is our data. And here, I'm going to put a little data over here. There's our data. There's like that. And wow. So we can just, haughty. We just can just do this thing. Open up this and come on. There we go. There's our data analysis tool pack. Lots of little fun tools in here. And we want to do regression right there. Regression. And we're going to do regression and open and okay. And, you know, pick the data. Here's the Y data. Here's the X data. Not too difficult so far. And where are we going to put the answer? All right. I prefer to put it right here. That's where I like to put it. So there's where the answer is. And lots of fun choices down here, and most of which you don't have any clue what they are yet. But the only one I'm going to worry about right now is the residuals. Let's plot the residuals. So plot the residuals, and yeah, that's it at the moment for now. Yeah, that's all there is. There's nothing else to do. So okay. OCO. There we go. Spread out these columns a little bit so you can read what they say. And looking good, looking good, looking good. Looking good. Looking good. And there we go. That was easy. Woo. Look at that. That was fast too. Man. Whew. Here's the ANOVA table that we spent all that time figuring out. Right there. There it is. Matches exactly. The order of the columns is not the same. Thank you, Mr. Gates. So, you know, every textbook I've ever seen, the sum of squares is the first damn column. It's like, but you know what they say, you know, Bill Gates, he dropped out of school, you know, so he quit school to start Microsoft. So I think that explains why these things are all wrong, because he clearly didn't go to class. He clearly didn't learn this in class. So, so most textbooks, this is the first column, but of course not in the program on Microsoft Excel. So degrees of freedom, sum of squares, our mean square, the F statistic, the F test statistic, and the p-value. This is the p-value. It says significance F, but this is the p-value. This is the p-value right there. And so at 5% significance, we're good. We're really good. We're fine. And then down here, below that, so we have the B null and the B1, the parameters. And this word intercept is you know, fancy word for B null. It's the intercept of the line at the x equals 0 point on the chart. And then we have our first and only x parameter, because this is simple regression. This is a simple linear regression, so there's only one. So this is x1, and then our parameters. And then we have some statistical tests here. We have some statistical tests, and we have the t statistic for these parameters. We have a p-value for these parameters. And this p-value for the B1 parameter is the same as the p-value of the regression here because it's a single linear regression. So yeah, they are the same. Later, in a couple of weeks, we're going to do this with multiple x values, and there will be multiple rows down here. And so then these p-values will not be the same as the total model. But right now it is. Today it is. They're the same. They are both the same. And then over here, we have 4 columns. These 2 columns over here are identical to these 2 columns here. I'm not going to explain why. It's not important right now. It's not important. And I'm not going to explain when they would be different. I'm just going to leave it. The first 2 columns are the ones let's care about. So this is the t statistic confidence interval. So this is work toy 3 or 4, can't remember which one exactly, but anyway, it's our t statistic confidence interval that we learned about, and that's exactly what this is here. And so we have a confidence interval over this value for this statistic. We have, because this is a random sample, remember guys, this is 5 data points. This is a random sample of some car dealer's sales over a period, and we just took 5 samples, 5 weeks, I guess, 5 weeks of sales figures. So it's a random sample. So it could be different. It could be, the parameters could be different than what we think they are. And in this particular case, they're enormously different. They're just like off the charts different. So we only have 5 data points. So our degrees of freedom is crazy 3. Our degrees of freedom is just 3. It's just crazy small degrees of freedom, right? And so we really don't know that much. And we had this beautiful model and the pretty picture and the line looks good and everything's, and the residual chart looked really beautiful. And we're like, oh, this is perfect. But wait a minute, hold on. No, we haven't actually learned that much here, because statistically, we have so little data that we really, this value of this parameter, it could be all over the place because this is a random sample. So we have a 95% confidence interval here that says we are 95% confident that the true value of this parameter, of this slope, will appear, I will say lies in, but as I explained a couple of weeks ago, that is actually statistically not really the correct way to say it, but we always say it anyway because we get lazy and we're tired of using so many words. But we are 95% confident that that this test, this sample, has the correct slope for this function in this interval, which stretches from 1.5 to 8.4. I mean, it's somewhere. It's like a positive number somewhere. I don't know where it is, but it's out there somewhere. It's a huge range. It's crazy, So this is an example of, and the reason it's such a big range is because our sample size is so small. The small sample size and the small number of degrees of freedom means that this t statistic right here is off the charts. It's an enormous t statistic. And then when we create the interval, the confidence interval, the plus minus, we have this great big number, and it's just driving our confidence interval to a crazy width. So this is So is it significant? Is this a significant model? Yes, it is. I can say with significance that the regression model I have created does explain the error. I mean, does explain the result. Yes, I can. Can I tell you exactly what the shape of that model is? No, I can't. No, I can't. It's a significant model. I am completely confident and significant that this model exists. I just have no clue whatsoever, really, what the parameters really are because there's not enough data. And this happens, right? And I'm pointing this out because this is important, because I'm saying, the research reports or analysis or various, Undersökelser, different studies, and they could do this and then only quote this number in the report and say, oh, we are so smart. Look, we found the significance is really good. We got the model. And then you look deeper, or maybe they don't even print it. They may not even tell you. They may not even give you the answer, which I think is really cheap. But maybe they show you this number down here, and you look at the table of data and you look at this number down here and you're like, you are 100% certain that you don't know what the answer is, and that happens. And you got to be careful about that, because especially, what if this is a parameter that's really important? I mean, what if you're making a decision based on this parameter? What if you are making a decision about whether to go ahead and invest in some big transport project, and whether or not the transport project is a success or a failure completely depends on exactly what is this number? And if the answer is, well, yeah, the number is positive, but we're not really sure where it is. And if maybe this number at the lower range means your project is a failure, that's important to know. That's important to know that, maybe you don't want to do this, that you're not really as certain about the success of this as you think you are. So you have to be careful about that. So anyway, and we will see more of this. This is going to be an important data set. I'm not the data set, but this is an important tool. This table of results and these confidence intervals. We're going to look at this a lot going forward, because we'll use it in things like stepwise regression and stuff like that. And this p-value and this confidence interval are related to each other. We will see that too. But what can happen, for example, is this interval can include 0. It can happen that you get a regression and you get a result, and the result says, oh yeah, your coefficient is 1.5 Teluga. And then you look at the confidence interval and it says, yeah, but our 95% confidence interval is that the value lies somewhere between -1 and +3. And the problem with that is that -1 to +3 includes 0. So you are 95% confident that maybe the actual value of this parameter is 0. So you are 95% confident that this parameter actually is completely worthless and has no value at all. And so that's important. We will see that over and over again as we work in larger data sets and more complicated data sets, that we need to start making decisions about, this data point that I put in here, this column of data, when I put it in, it makes a really pretty model. It has a really nice picture that I really like. But oops, when I look at the statistical table, the result says, no, this data column, actually, you don't know. You really don't know if it actually is worth anything or not. So this is important. So, and finally on this, I thought I plotted it. Where's the plot? I'm sure I tricked that. You saw me push that button. Oh, maybe I didn't. I thought I did. Anyway, I was sure I did. I've got it on another picture. But anyway, so here's the residual output. Those are the residuals. And I've got it. I can just copy it from another picture. Oops. I can just copy it from another. Well, where is it? Here we go. I can just make a quick copy. It looks like this. Here's Where is it? I've got it over here. I know I've got it over here. I'm sure. Well, maybe not. I thought anyway. Oh, there it is. Here, I'll just make a copy. I wonder if it's over there on my screen over here. No, it's not. I don't know. I must have forgotten to check a box, but there is a checkbox on there. Let me just take a look again here. Maybe I forgot. Huh. Oh, yeah, I forgot to check this box. I checked this box, but I didn't check this box. Yeah, so you check that box, and if you do that, it gives you this picture. I'm just going to copy and paste it from my solution over here. Copy and paste. Come on, paste picture. It looks like that. That's what it looks like when you plot it. So there's the residual plot that Microsoft generates. And of course, it's exactly the same as what we did by hand here before the last couple of coffee breaks or whatever. So anyway, good. So that is that. And now, now, where are we? We're coming up to the end here. We don't have too much more. Couple of things to study. We don't have to do this by hand. This will go pretty quick. We're wrapping it up here. Something called the coefficient of determination. And in the next couple of weeks, I can't remember, somewhere, we have the coefficient of determination, which is the R square. And then down below here, let me get a little pointer action going here. A little spotlight. There we go. And then down here, we have something called the adjusted R square. And I'm just gonna, I'll say something more about that in the future, not now. We'll just leave it alone. But the R square, this is a really important number that people quote all the time. So this is a number, again, this is a way of saying, okay, how much is my model really contributing here? And so here it is the ratio of the regression sum squares to the total sum squares. So in a way, it's another way of saying how much is the regression really contributing to this whole thing here, to this whole model. And so here, and there it is, there's the number. And then this is the Excel printout. This was in the Excel printout from the Excel data analysis pack. So it's R square, and the higher the number, the better. We want a high number. We want a high R square. That's what we want. The higher that number, the more you argue that, yes, your model is in fact covering things. But it's dangerous. It's very dangerous because, again, people will quote results with, crazy high R square like 0.9 or 0.95. And then you dig deeper, you can get a very high R square, even though the results on that ANOVA table or the results on that confidence interval for the individual parameters are not so good. That's the danger. The danger is you just quote R square and say, look, I succeeded. When in reality, underneath that R square is just garbage, is just potato chips and soda van. I mean, there's nothing there. So coefficient of determination, which is called R square in the Microsoft printout and in many textbooks. Coefficient of determination, this is a fancy statistical word, whereas almost everybody in the trade just says R square. So, stuff happens like that. And then we have the correlation coefficient, And so this is related to R square, but we want a slope. We want a direction to it. And this is another way of visualizing. People don't quote it as much. That, I'm going to show it to you here in the textbook, but to be honest, honestly, don't see it that often. It's, a few people use it for something, but in typical stuff we do in transport, nobody will care. Nobody's going to look at this. I never look at it. It's not interesting to me, but there are certain fields where this becomes interesting or it becomes important. And so they do use it, but just not particularly in any research or anything I do. But here it is. It comes out automatically in the Excel report, and it's directional. It has a sign. It has a positive or a negative sign, and that sign is achieved by just looking at what is the sign of the regression parameter, which you can of course calculate just with this little trick here. Take any number and divide it by the absolute value of the number, and that will give you a positive or a negative 1, which is the sign. Neat trick, huh? Yeah. So that's that. Not much to say about that. Here's a pretty picture of what the results could look like. So these are the different ways that could come out. And you have a swing between 0 and 1 of how good a correlation it is. And then you have a sign, positive or negative, that just tells you which way is the slope on the line. So, not too tough. But again, like I said, the paper we read from Lee 2016 doesn't use it. It's not. I don't believe it shows up in their results because it's just not. But for some fields, it's important. For some fields, they refer to this a lot. Actually, I've already talked about this. So this is what I was just talking about on the Excel output. So I kind of already did this. And here's how it's done. There's the solution from the ANOVA table. And this is the formula that is being used on that Excel printout to generate those results. So when I just finished talking about how the beta 1 parameter could be between 1.5 and 8.4, that came from this. That's how they calculated that. This equation did that. And yeah, there's no point in us doing this manually. I think we got the handle on the manual part, on the manual calculation. We're good. I think we're done presenting our ability to work with the calculator and our pencil. But it's just, just to let you know, where is that coming from? And it's coming from this. And this is it's the same kind of test statistic and kind of deal. And it's the same kind of, it's a similar, where's that p-value coming from? For example, where's that p-value coming from next to the parameter? It's coming from this. So again, it's another kind of t statistic hypothesis test, t statistic confidence interval. And the purpose of that p value is to argue, is this parameter 0 or not? The null hypothesis is that parameter is 0. And the alternative hypothesis, the not null hypothesis, is that yes, this parameter actually is worth something. This parameter is actually a real value. And so finally, this is the printout from the Excel spreadsheet right there. And I think we're about done. I think I had suggested something, but I think this is good. I think we've done enough. We've gone 3 hours. That's enough. So what we will do next week. So this is for next week. I'm going to push this picture to next week. I've got a data set that I put up on DTU Learn from Minnesota highways from the textbook. And we will kind of work with this next week and do a little bit more. And so we'll do that next week. And what we will do, so I'm going to skip over this, let's skip that. So what's going to happen next week? So now we've got these kind of fundamentals. And so now next week, let's try, I want to switch over to kind of working in parallel with Excel and R. I'm going to start working with R. And I think the way to do that is to repeat some of these basic exercises in R. Hopefully that'll only take, we'll install R get the thing to turn on, figure out how to get some data into R, and then do some of these things we did in Excel, but in R instead, so that we see them side by side. And then we'll do this Minnesota highway data. And again, what we'll do is we'll do it in Excel and in R, side by side, in kind of, I mean, not literally, but we'll do Excel and then we'll do it in R, and then we'll do it in Excel and then we'll do it in R. And so Excel, so you can see the answer in R, but then you can check it in Excel and prove to yourself, yes, I got it right. I did it correctly. So we'll do that. And we'll take a look at the homework, solution and stuff next week. And that's about it. Yeah, let's call it quits for now. So thank you for today. Thank you very much. And have a great time. Hedigat. And we'll roll to next week. Let me check with the, yeah, and yeah, yes. So that's, yeah, I think that's it, guys. So enjoy. See you next time. And be safe. So I'm signing out. See you later.